Hey everybody, so we're going to go ahead and continue lesson 2.4. If you were here on Friday or even if you weren't, let's go ahead and do a quick recap and then we'll jump into the new stuff. On Friday we talked about variation. Simply put, variation is how spread the data is. As you can see in Corporation A, most of the data is pretty compact, centered around 43.5, whereas in Corporation B, there is a lot more variability to the data. So this is the main idea of variation or spread. You're going to hear both. We then talked about some formulas, including deviation, which is not standard deviation. Those are different, but they're closely related. And we have two formulas here, one for the population, which is this one, and one for the sample data, which is this one. They are very identical. The only difference is, remember, mu stands for population mean, and X bar stands for sample mean. Then we talked about these two formulas that look scary at first, but we practiced it on Friday. And basically, the thing you need to take away is that population variance is denoted by sigma squared, and population standard deviation is denoted by sigma. So on a test, on a homework, if you see this symbol here, it's population variance. And if you see this symbol here, it's population standard deviation. Then we talked about if you have one of these, you can easily find the other. For example, if sigma squared is 25, well then I can find that sigma is 5. And you can go forward and backwards with these. So you don't have to use both formulas. Once you find one, you can basically find the other with just one more step. And then here was the example that we did in class, where basically you had to do each step with each data entry. So you can grab all the data entries and subtract by mu, and you can see that's what we're doing here. And then after you do that with each data entry, now you're going to go ahead and square each data entry, which is what we're doing here. And once you square everything according to the formula, now you have to add all these up. So we're going to add up all these right here. And when we do that, we get 88.5 for this top part. And capital N, remember, if you don't know what that is, please write it down. Capital N is your population size. And it's 10 because we had 10 data values in our example. Now rounding, we get 8.9, so we would write sigma squared is equal to approximately 8.9. And once we have that, we can take the square root of both sides, and we'll get that sigma is about 3.0. I think if we actually take the time to calculate this, you're going to get about 2.7, somewhere around there, or 2.97 if I'm not mistaken. But that's the main idea here. Now, it's important to note that both sigma and sigma squared just stand for population variance and population standard deviation. Okay, we're going to use these symbols a lot in this class, so when you see these symbols, it's very important you know what they represent. Now, for standard deviation has the units that the problem has, that the data has. So if you remember, we were talking about salaries. So this 3.0, it's not just a number, it has units to it. And everything in the problem that we were talking about was in thousands. And it was in money. So this 3.0 really represents $3,000, which means that the population standard deviation is about $3,000. Now, variance, on the other hand, does not have any units. All right, so variance has no units. Sigma does have units. And the reason why variance doesn't have any units, in case you're wondering, well, it wouldn't really make sense to say that the variance is 8,900 dollars squared, right? That wouldn't make any sense. So that's why we don't have units. How are we going to square money, right? Like, that doesn't make any sense. So variance never has any units. Standard deviation always has the units that the data has. So if the data is in inches, so is the standard deviation. If the data is in money, dollars, then so is the standard deviation. All right, and just how we have population variance and population standard deviation, we also have sample variance and sample standard deviation. So here are two formulas that you're going to go ahead and write down on your paper. And by the way, if you weren't here on Friday, I did not hand out lesson notes. I'm actually having you guys write these. And the reason is I want you guys to practice writing what's important, and I want to prepare you guys for college classes that typically are done in 50 minutes, and the instructor doesn't answer a whole lot of questions, nor does he or she take a lot of pauses. So let's practice taking good notes. Of course, you have the luxury of pausing this video and going back anytime you want. But yeah, I want to prepare you guys for that. So right away, hopefully you see that there's a lot of similarities between this formula and the population formulas. So if I remember correctly, the population variance formula was like this. And the population standard deviation formula looked like this. You can see if you compare each of these formulas side by side, they're pretty much identical. The only difference is some change in symbols. So for example, sample variance, we're not going to use sigma squared anymore because sigma squared was for population variance. So what we're going to use now is S squared. Okay, so sample variance will be S squared, and sample standard deviation will be simply S. Now another symbol that changed was this symbol here, X bar. In this formula, it was mu. Well, that makes sense too because X bar is the sample mean. And we are dealing with a sample variance. Whereas mu, again, was the population mean. Same thing over here, right? X bar is right there. That's the sample mean. Now, the last part that changed is this bottom part, the denominator of each formula. Now, if you remember correctly, capital N was the population size. Well, lowercase n will be the sample size. The only thing we need to remember is that when we use this formula, we have to subtract 1 from the sample size. And the reason is actually pretty complicated, but it has something to do with the topic called degrees of freedom. It's something we will talk about hopefully later in this class. But for now, all you need to know is that for sample variance and sample standard deviation, you're going to take your sample size and subtract 1. Okay, so we're going to go ahead and try this problem out. I encourage you to pause the video here, read the problem, try it out, and then after a while you can go ahead and unpause to see if your solution was correct. All right, so hopefully you tried that out. Let's go ahead and jump into this. Mainly what happened is we have a data set here, and we are asked to find the sample variance and standard deviation. So because I see the word sample there, I immediately know which formula to use. And that's going to be something you guys have to be able to figure out as well. Should you use the population formulas or the sample formulas? And more often than not, it'll hint towards it in the problem. If not, they'll flat out tell you, like they do in this problem. All right, so let's go ahead and one last thing before we jump into it. What units are we using? These numbers are a representation of what? Well, these are days. So this is 10 days. This is 7 days. So keep that in mind for when we calculate standard deviation and variance. All right, we're going to go ahead and follow the formula. And first thing we're going to do is take all of our x values, right, all of our data entries, and subtract the mean, the sample mean. Okay, so we're going to take all these x values and subtract the sample mean. And this is what we get after we subtract the sample mean from each data value. Okay, once we have all these, we're going to go ahead and square them. And it's how we get these values. Okay, so we're going to square everything. So negative 3.5 squared is 12.25. You notice that some of these numbers were negative, but at the end, after you square everything, there should be no more negatives left. So if you have any negatives left in here, something went wrong, either how you typed it into the calculator or something else. But the whole point of squaring is to get rid of these negative values. All right, once we square everything, we're going to go ahead and add all these values together, and we will get 39. All right, so now we have 39, and we're going to go ahead and divide by n minus 1. Now remember, there is 12 data values, n is 12, so instead of dividing by 12, we're going to divide by 11. And that's how we get 3.5 for the sample variance, so we can write s squared equals 3.5. Remember, no units on this, and s, we just have to take the square root of that. S is approximately 1.9. Now remember, there are units on standard deviation, so this is going to be 1.9 days, which means that the average, distance from the mean in terms of recovery time was 1.9 days. Now, we can also use technology to find standard deviation, and that's actually something I'm going to show you guys when I return. But there will be a way to check your answer. That way or to do this with technology, because imagine calculating standard deviation or variance for a larger data set like this. When you have 10 numbers, that's fine, but when you start getting upwards of 20, it really becomes tedious. So I will show you guys how to calculate this with technology, and it'll make everything so much easier. All right, a big part of this class last semester and this semester is interpreting standard deviation. Now, last year we had a template, and you're welcome to still use that template. But it's also a good idea to understand what it is and not have to rely so much on the template. So let's go ahead and look at each of these examples. That symbol. Take a second. What does that symbol mean? Hopefully, you got that is the sample mean. Right? Again, these numbers are not going to make sense if you don't understand what the symbols represent. So this is the average of the sample. We can see that there are 8 data entries of 5. So that means there's 5, 5, 5, 5, right? There's 8 of these. Now, obviously, if you have a bunch of 5s and you add them all up and divide by 8, you're still going to get 5, which is what they got there. And because there is no variation here, right? They're not spread out at all. We get that the sample standard deviation is 0. That's because they're all together. They're literally the same value. There is no variation there. But if you look at this example over here, the sample mean is still 5. But as you can see, they are a little bit more spread out. So the sample standard deviation here is 1.2. Now, if we look at this example, again, the sample mean is still 5, but these are even more spread out from the mean. Standard deviation is all about how spread out you are from the mean. So if in all these examples, the mean is 5, we are calculating how spread out everything is from the mean. So here the mean is still 5, so the mean is in here. You can see that things are a little bit more spread out, which is why you have an even larger standard deviation of 3. All right, so if you're going to take anything away from this slide here, it's that standard deviation is a measure of the typical amount of entries from the mean. That's very important. Okay, this is measuring how far data values are on average from the mean. Not the median, always the mean. All right, so now what we want you to do is go ahead and look at all these and estimate. You're not going to have your calculator out for anything. Just estimate what is the population standard deviation of each data set. So what is sigma going to be here? What is sigma going to be here? And what is sigma going to be here? Okay, take about a minute or so, pause the video, try both of these out, and then come back to see if you were correct. All right, let's look at the first one. In the first one, we need to know what the mean is. Well, remember that symbol? That symbol is population mean. All right, so the mean here is 4. And all of the data values are 4. Therefore, there is no variation. Therefore, the standard deviation of this data set is 0. There is no variation. Let's look at number 2. Again, the mean here is 4. So if I draw a line where the mean is, right, that's the mean. You could see that there is some variation here. So we definitely will get a number bigger than 0. But you can see that these data values are exactly +1 because they're all at 5, right? These are all +1 away from the mean, and these are all -1 away from the mean. Therefore, your standard deviation has to be 1. Because on average, these data values are 1 away in either direction from the mean. And if we look at the third and final example, again, the mean is still 4. So let's go ahead and draw that in there. But now we have a little bit more variation where these are +1 and these are -1. But then these here are about +3 and these are -3. So again, the distance for these data values is +1 and for these is +3. For these it's -1 and for these is -3. And they all have a frequency of 2. So then we can see that the average distance from the mean should be somewhere between 1 and 3. Okay? And actually, if you calculate this, it would be about 2.2. So as long as you set around 2, you get the idea. And here are each solution. So if you want to go ahead and pause the video and read these, by all means. And then here is the third one. Okay. Now we're going to talk about the empirical rule. This is something that we did talk about last semester. So I hope this is, something just of a refresher. But it is important to remember that this only works for data that has a symmetric bell-shaped distribution, which looks like this. All right. if the data is not distributed in this manner, it will not work. So if I go backwards and look at this data, this is clearly not bell-shaped. Empirical rule will not work here. This is not bell-shaped either, right? And this one is definitely not bell-shaped, although you can kind of force it to be, but because the only data entry is 4, and it is not bell-shaped. Bell-shaped would look something like this, right? That'll be something more bell-shaped. Okay, so assume we do have a distribution that is bell-shaped. Then the following characteristics are true. About 68% of the data lie within 1 standard deviation of the mean. That's plus or minus 1. So if you want to draw your picture, and again, we drew one of these last year, so if you have that in your notes somewhere, you just want to copy it, go ahead. But notice it's from the mean. So let me just, for the mean, let me just use mu. Right? So 1 to the right would be mu plus 1. 1 to the left would be mu minus 1. And within here, we have about 68% of the data. Now, 95% of the data lies within 2 standard deviation. Again, that's plus or minus 2. And 99.7 lies within 3 standard deviations, plus or minus 3. If we draw out a picture, you should get something that looks like this. And this is actually what I encourage you copy down onto your paper. So go ahead and pause the video here. You notice instead of mu, they're using x. They're using the sample mean, which is totally fine. And they're using S for standard deviation. Again, what they're doing is they have the mean and they are adding 1 standard deviation. They're taking the mean and they're adding 2 standard deviations. And then same thing the other way. They are subtracting 1 standard deviation. So that's what's going on here. So we can go ahead and use this to estimate the percentage of a population over sample that belongs to a certain category. So I want you to go ahead and pause the video. You don't have to copy this down word for word, but if you want to, go ahead. Pause the video, try this problem out, and then come back to see if your answer was correct. All right, so when you're looking at these problems, you should start looking for key information. We have the sample mean height is 6.2 inches. So that means X bar is 64.2 inches. Remember, X bar, not mu, because we're talking about a sample. The sample standard deviation is 2.9. So that means that S is 2.9 inches as well. Now estimate the percent of women whose heights are between 58.4 and 64.2. So you're going to have a picture like this, and you will have a region that you will shade in, and you're going to calculate that region using the empirical rule. So it should look like this. Now, it's important to realize that we can use this empirical rule because it told us in the problem, let's see, well, I guess it doesn't tell you in the problem here, but it should normally tell you that your data is bell-shaped, or it'll say symmetric, maybe it'll say normal, right? But these are the conditions needed for us to be able to use this empirical rule. Now, obviously here it says use the empirical rule, so if it tells you to use it, you don't have to worry about it. But that is a condition that has to be met for the empirical rule. The first thing you would need to do is find all these numbers that go down here. And then shade in the correct region. Using the empirical rule, we get that 13.59 is there, 14.13 is there. We can add those two together. And we get about 47.2% of women are between 58.4 and 64.2 inches tall. All right, this next one, we will not have to worry about it, so I'm going to go ahead and skip this one. Okay, next we're going to talk about finding the standard deviation for grouped data. So what do you do if you do not have every single data value in front of you? So for example, let's say I have a table that looks like this. Let's say that these are my classes. So let's say these are the classes, 0 to 4, 5 to, okay, so 10, 15, okay, so let's say these are my classes, and the frequencies are as follows. Well, I know that there are 3 data values between 0 and 4. I know that there are 4 data values between 5 and 9, but I don't know exactly what they are. These could be, so if I look at these here, it could be a 0, a 0, a 0, or it could be a 1, a 2, a 3. I really don't know. I know which class they belong to, but I don't know exactly what they are. So this right here is called grouped data. When you don't have all of the data values in front of you, how do you calculate standard deviation? Well, this would be the new formula for grouped data. So copy it down, take a moment to try to read this formula, try to translate it to English, and then we can talk about it in a little bit more detail. Okay, so hopefully you copied it down. You're trying to understand what it is. Before I go over it in full detail, I want you to try to complete this example on your own. Now, I know it will be a little bit challenging, so let me start you off. You have all this data here, right? I want you to first go ahead and construct a frequency distribution table. Right? So meaning how many zeros do you have? How many ones do you have? How many twos? All that. So So 0, 1, 2, 3, 4, 5, and 6. And the reason we're not using classes is because all of the data values are between 0 and 6, right? So it wouldn't really make sense to break these up by 0 to 1, 1 to 2, all that. So how many zeros do we have? Go through, pause the video, fill out the rest of this table, the frequencies. All right, hopefully you got that there were 10 zeros, there were 19 ones, there were 7 twos, 7 threes, 2 fours, 1 5, and 4 sixes. All right, so now what we're going to do is multiply x times f. So multiply x times f. And we're going to get 0 here, 19 here, 14, 21, 8, 5, and 24. All right, and if I add up all these x times f's, we're going to get 91. So if I were to add up all these, you get 91. And now we're going to go ahead and find the mean of this. So the sample mean, remember this is your formula for grouped data. 91 divided by your sample size, there were 50 numbers. And you can get that by adding up the frequencies. All right, there are 50 numbers. So we're going to go ahead and divide by 50. And I get that my sample mean is 1.8. Now, why did I do all this work? Well, if you look at the formula, you're going to need your sample mean. Right? So now we know that that is 1.8. Now, yes, you could have just added all these numbers and divided by 50, for sure. But sometimes building a table and organizing the data can be a better option, especially if you're going to need to use the table for other stuff down the road. So if it's a large problem, maybe organizing it first is a better move than just keeping the data unorganized. So all that work, we found that the sample mean is 1.8. And the units on this is 1.8 children. Because we're talking about the number of children per household. So on average, there is about 1.8 children per household. All right. So now I can actually go ahead and do the rest of the formula. So what I'm going to go ahead and do is take all my x's and subtract the sample mean, square that, and then multiply by the frequency. All right. So it's going to look like this. You take all of your data values, subtract your sample mean from each data value. You're going to get these numbers here. Again, you get some negative values, which is okay, which is why we're going to square everything. And we should have no more negative values. And then we're going to multiply by 10. Now, why are we multiplying by 10 here and by 19 here and by 7 here? Why are we doing all this? Well, the reason is, if you go back to this table here, we have 50 data values. Imagine trying to calculate the standard deviation for 50 data values, right? That would take forever. You guys did it earlier for like 10 or 12 data values. Now imagine 50. Well, without technology, it is a really cumbersome task. But if you get a lot of repeats, so for example, we got 10 zeros. We got 19 ones, right? We're getting a lot of repeat values here. So when we get a lot of repeat values, what we can do is just do the steps we would for one of the values. So there are 10 zeros. Just do it for one of them. And then at the end, multiply by however many of that data value there is. So because there are 10 zeros, I can just do this with 0, right? And then at the end, just multiply by 10 because there's 10 of them. I'm going to get the same result. I'm just going to get it 10 more times. Same thing here. There are 19 ones. So I could just grab the 1, the actual data value, go through the steps that I normally would go through, and then at the end, multiply by 19, because there's 19 of them. Same thing here. 2, calculate all these steps with 2, then just multiply by 7, because there are 7 2's. This is a much faster way than having to do 0 10 times, 1 19 times, 2 7 times, right? You just do it that one time and then multiply it by 10, or by however many data values there are, by the frequency of that data value. Now once you do that, you can go ahead and add them all up, and you're going to get 145.38. Of course, it's rounded. Remember, n here was 50. So we get that the sample standard deviation is about 1.7 children. Now, what would you do if you didn't have all of the data values like we did in this table, right? Here we had every single data value. So how would we calculate all this when we don't have all of the data values? Well, it's simple. It says it right here. When a frequency distribution has classes, right? So that was like this example over here. When you have classes and you don't know all the data values, you can estimate the sample mean and standard deviation by using the midpoint of each class. Right? So that's where you would add a separate column of the midpoint. So for 0 to 2, right, you're going to do 0 plus 4 divided by 2. You get your midpoint is 2. So you would do, instead of x minus sample mean, you're going to do 2 minus sample mean. And then multiply that by 3 because there are 3 of those, right? Similar steps, except you're using a midpoint instead of an x value. So instead of using an x value here, you would do the same exact steps, except this would be like the midpoint. And it's the same exact steps. You just use a midpoint instead. All right, so now we have another example exactly talking about the midpoints. So now we're going to go ahead and use the midpoints of classes. So again, pause the video, go ahead and read the question to yourself, try it out, and then we can go over the solution. All right. So there's a couple things you have to do. First thing you have to do is make a frequency distribution for the data. Then you have to use the table to estimate the sample mean and sample standard deviation of the entire data set. You know that there are 1,000 adults, so that means that lowercase n is equal to 1,000. You have all the data in this image here. So go ahead and make a table. So begin by using a frequency distribution to organize the data. Because the class of 500 or more is open-ended, you must choose a value to represent the midpoint, such as 599.5. So this is what we mean here. You see that in this example, right, the classes are literally given to you. 100 to 199 is one class. This is the second class. This is the third class, fourth class, fifth class, right? I guess technically this is the first class here. Second, third, fourth, fifth, sixth class. Because this last class is open-ended, meaning it doesn't have an upper limit, you kind of have to choose what you want your midpoint to be. Now here they chose 599.5, and that's okay. This is where the whole point of estimating is going to come into play. All right, so you're going to have to estimate these midpoints when the class does not have an upper limit. So if you build your table, this is what it should look like. Where these x values, again, we don't have all the data values, right? So instead of these being data entries, we don't have all the data entries. So these are the midpoints. We're using the midpoints because we don't have the data entries. So the midpoint of this class is 49.5. The midpoint of this class is 149.5. And we know that within this first class, there are 380 data entries. We don't know what they are exactly, but we know that there's 380. We know that there's 230 in here, right? So because we don't know, we're going to use the midpoint and multiply that by the frequency to get these numbers here. And all this is to calculate the sample mean like we did in the last example. So we get that x bar is equal to 192. Now we're going to use that for our formula. So we go back to the problem, calculate the sample mean, check. Now we're going to calculate the sample standard deviation using that formula from earlier. Okay, so we're going to take all of our midpoints because we do not have each data entry, and we are going to subtract the sample mean. And that's what we have in this column here. Then we're going to go ahead and square all these numbers so they turn positive. And then we're going to multiply all of these numbers by the frequency of that class. So, for example, this first number, we're going to multiply by the frequency, which the frequency of the first class was 380. So this is times 380. This here will be times 230. And that's how we get all these values. Once you do all that, add them all up, and that's where you're going to get a really big number. And then we can divide by n minus 1. Remember, there n was 1,000, so that's why we're dividing by 999. Then take the square root, and we get 160.3. Now remember, this should have units, so what are the correct units on this problem? Let's see if you can figure it out. If you said dollars, you would be correct. So $160.3 per year is what we're talking about here. All right, $160.3 per year. And the mean was $192 per year. All right, now we're going to talk about the coefficient of variation. Now this is a very easy thing to calculate. There are two formulas, one for population, one for sample. But as always, they are identical. You just need to know if you're dealing with a population or a sample. What this does is describe the standard deviation of a data set as a percent of the mean. Now, we did have notes on this last semester, but it's okay if you don't remember this exactly. Let's just copy down the formulas and remember what some of this stuff is. So this is your population standard deviation. This is your population mean. This is your sample standard deviation. This is your sample mean. Using these formulas is really straightforward. But sometimes you do need to calculate the sample, either means or population means, or sometimes they're going to give them to you straight out. So for this example, you're going to go ahead and calculate the coefficient of variation for the heights and weights, both of them, typo, heights and weights, and then compare the results. So here's the data set. Go ahead and try it out. Okay, so you do have to calculate the height, the mean height, and I know to use mu because it says population heights, right? So we're talking about a population, not a sample. Mu is about 72.8 inches. Standard deviation is about 3.3 inches. Sometimes they're going to tell you these, sometimes you have to go out and find them. And these are for the heights. So if I use my formula correctly, remember it's CV, and I'm going to put height here because we have height and weight going on. Sigma divided by mu times 100% is equal to 3.3 divided by 72.8 times 100%, which is equal to about 4.5%. What we got here. And then for weight, well, for weight, you'd have to do the same thing. Mu is about 187.8 pounds. Sigma is 17.7 pounds. Calculate it the same exact way. Notice they put weight now because you got two coefficient of variations going on. And now we can compare them. So the weights with 9.4 are more variable than the heights with 4.5. Basically, the weights vary more than the heights vary on this basketball team.